So you can start now.
Are you able to see the slides?
Yes, sir, it's coming.
Yeah. Oh. Thank you very much, and good afternoon, everyone. And the title of today's talk is Automated EEG Signal Analysis and Classification. So here we will see the use of advanced signal processing techniques like empirical mode decomposition and time frequency analysis techniques like Wavelet distribution, and for the analysis and classification of EEG signals. We will also see use of multi-wavelet decompositions for the classification of EEG signals. And actually, the signal processing techniques that we will see in this talk, they are very useful for providing the features. And these features actually they are very nice. They have very nice applications for the interpretation of the data. Like in biomedical signal processing, the two parts are very important. One is analysis, second one interpretation. So once you have performed analysis, and after analysis you have to interpret. So these features, whatever you extract using signal processing, they play important role for the interpretation of that disease. Like what is the stage of the disease? It is severe or normal, or it is very like moderate. So the different kind of actually stages can be detected, and they can be correlated with the features. So these features are very important, and the signal processing techniques, they can provide you a nice set of features. And once you have these features, then you can give these features as an input to machine learning classifiers, and nicely automated identification systems can be developed based on these features, and in that way the disease can be identified. And such kind of systems are very useful specifically for rural areas where we don't have doctors, and such systems, such algorithms actually can be installed in the form of software in the computer, in the smartphone, and a smartphone will become really smart, and it can like detect disease in the beginning itself, in the initial level. And we can also install these algorithms in the computers, laptop, and this neurologists, doctors, they can use these algorithms for assisting them. And so then this can be helpful for the efficient diagnosis of these doctors, performed by the doctors. And in this talk, we will see three main actually parts, three types of actually EEG signals. One is like for epileptic seizures, and second part is sleep stages, and third part is the emotions. So in these three cases, we will try to analyze and classify signals of various classes and various categories. They may be like different sleep stages. This may be seizure, normal. It can be different kind of emotions. So these all are very useful actually for healthcare technology. For like a brain is a master of the body, and understanding brain is very useful. And in order to understand brain, the EEG signals play important role. They measure electrical activity of the brain. So here we will see how the signal processing and machine learning algorithm together can be used for the automated identification systems for assessment of the electrical activity of the brain. With this background, let us start this talk. So this first actually in this talk we will see introduction, what is the motivation for using EEG signals, for studying EEG signals, and what is the motivation for applying signal processing algorithms, machine learning algorithms. And after that we will see empirical mode decomposition based features for analysis of normal and seizure EEG signals, and after that classification of seizure and non-seizure EEG signals, and then detection of epileptic seizures. And after that, time frequency image based features for a classification of sleep stages. So we will see how this actually time frequency distribution can be used as a time frequency image, and then we can extract features, and then these features together with machine learning algorithms can be used for the identification of sleep stages. And after that, multi-wavelet decomposition based features for human emotion classification, and in the end conclusion will be provided. Human brain is a very complicated, it is highly complex and nonlinear system. These EEG signals Actually, they measure the electrical activity of the brain, which is generated by the neurons. And for example, if you record EEG signals in the morning time, and when you are having happy emotion, and same emotion, happy emotion, suppose you have in the afternoon, and you record EEG signals, you will not have same EEG signals, because the subject is same, but at different times the signals are different. So they are actually highly subjective in nature. They change with time. They are different times, these signals are different. So these signals are having very high variability, and due to that, actually understanding these signals is not an easy task. And sometimes these signals look like chaotic, they look like highly non-stationary. So due to that, actually extraction of information using EEG signal is not easy. And EEG signal is a valuable clinical tool in order to investigate different physiological and pathological states of the human brain. And if you have any problem related to the brain, and if you go to hospital, doctor will ask for EEG signal. So EEG signal is the first signature which is actually required to assess the electrical activity of the brain, to understand about the state of the brain. And suppose you are having stress, you are having anxiety, you are suffering from depression, and you go to neurologist, they will first see your EEG signal. So once EEG signal is abnormal, then they will go for higher level of treatment. So this is the one kind of actually basic analysis, basic part of brain diseases, this EEG signal analysis and classification. And quantitative analysis of EEG signal is a challenging task because of this complicated signal, and it is highly irregular nature. Because when you see EEG signal, it doesn't have regular pattern. It doesn't have any deterministic kind of nature, and it is actually non-stressy signal. So like in signal processing, we use mathematical models to represent the signal. If any of the parameter of these models are changing with time, then we call it non-stressy signal. And it has been shown in the literature, even if you take EEG signal for very low scale, for very less time interval, then also it is non-stationary. It is very difficult to obtain the stationary EEG signal from the given EEG signal. So that is why whatever scale you use for analysis, the signal is always non-stationary. And what actually we do generally when we go to hospital, and doctors actually they record your EEG signal, and they print the signal on the paper, and then they perform visual scanning of the paper, and that method is very time consuming. And because for example, like you are at someone is admitted in the hospital and in ICU, and entire night this EEG signal has to be printed, has to be recorded, and you want to display on the paper. And sometimes signal is of 2 hours, duration of 2 hours, and 2 hours printout you cannot see anything. So it is difficult actually to perceive the changes when you have a large interval of time for the recording. And sometimes it is difficult also, and every time the person is needed to monitor the EEG signal, and it may be inaccurate also. Like when you are taking EEG signal or recording EEG signal for a lot of time, it can be inaccurate, and it is very complicated, and it is that subject to judgment and suffers from human error. For example, like if you must have seen that when this one neurologist say that you have this problem, and then actually patient says, let us have opinion from other neurologists. So the analysis or subject, whatever this detection of the disease or diagnosis of the disease based on the visual scanning, that is actually subjective in nature. So different neurologists can have different opinion on a given signal or given EEG signal. So due to that, it may suffer from human error, and the judgment whatever is actually provided, that is very subjective in nature, and it is performed by the trained professionals. Like they have got a specific training, and they are expert actually, and they perform such kind of diagnosis. And real life, this disease doesn't see whether you are expert or you are engineer, doctor, or you are professor, or you are educated or uneducated, illiterate, whatever. This disease can go to anyone. So that is due to that, this whatever methods we use, that can be used by the common person. Then is actually the real use of the technology for the healthcare. Because that is why due to this reason, the signal processing and machine learning based methods, they are very, very useful. And these days there is a lot of scope in this area where we can develop automated systems based on the signal processing machine learning algorithms for the classification of EEG signals. So in that way, these systems, whatever you develop, they can be used for the initial detection of the disease. So once you detect disease at the initial level, then actually you can go for the further treatment to urban areas, or to go to hospital that is close to your native place. So that is actually in that way, this is the motivation for employing signal processing and machine learning based techniques for analysis and classification of EEG signals. So the first part that we will see epilepsy, and that is actually, we will see analysis, classification, detection of epileptic seizures. So epileptic seizures, which is also known as epilepsy, is the outcome of the transient and unexpected electrical disturbance of the brain. So in human brain, these all neurons, they synchronize together and they generate very high electrical activity. And due to that, this actually, when you have this high electrical activity, due to that, brain is the master of the body, and it disturbs the brain. And once brain is disturbed, then all parts of the body, they are disturbed. So entire it affects this very serious disease, and this human system becomes non-working kind of thing. They are like it is once you have epileptic, then this is due to this attack, this everything is disturbed in the body, and it affects around 2% population of the world. And for this in this area, for this diagnosis of epilepsy, we have proposed area parameter for analysis of normal and epileptic seizure EEG signals. And we have also proposed bandwidth parameters for classification of seizure and non-seizure EEG signals, and the instantaneous area for the automated detection of epileptic seizures. So we will see in detail in this talk. So this is the overview of these techniques. These techniques actually they are based on the empirical mode decomposition. So that is actually it is proposed. It was proposed in 98, and let us give you brief overview of the signal processing before starting this EMD method based technique. And the first technique actually that is commonly used for signal analysis, and that is Fourier transform. So what actually we do with Fourier transform, we represent signal in terms of sinusoidal functions, and these sinusoidal functions they vary from -infinite to +infinite. These sinusoidal functions are periodic in nature, and the duration of sinusoidal signal is infinite because due to this periodic nature. And resolution, time resolution, concentration, and focus of these basis functions like sinusoidal functions, that is proportional to 1 upon area, 1 upon duration. And duration of the sinusoidal signals in time domain, that is infinite. So due to that, the time resolution is 0. So these non-stressy signals like EEG signals, they are highly non-stressy signals, and their parameter, their properties change with time. And these signal basis functions, like in case of Fourier transform, the sinusoidal basis functions, they are not changing with time. They are always periodic. They are same every time. So due to that, time resolution is 0 in case of Fourier transform of these basis functions. So due to this property, these basis functions are not able to represent non-stationary EEG signals in efficient manner. So in order to apply this Fourier transform for non-stationary EEG signals, that short time Fourier transform was proposed, that is STFT. That STFT, short time Fourier transform. So what we do, we actually divide the signal into different windows, different segments, and each segment we assume that signal is stationary, and then we apply Fourier transform to different segments, and arrangement of these Fourier transforms gives you the short time Fourier transform STFT, and that is square magnitude of STFT gives you spectrogram. In STFT, there is actually one of the important serious problem that is the selection of the type of window and size of the window. So there is no thumb rule which will suggest you what should be the size of the window and what should be the type of the window for analysis purpose, signal analysis. Like if you have a low frequency component present in the signal, then you need wide analysis window. And when you have high frequency component present in the signal, then you use narrow analysis window. And that flexibility is not available in the STFT, short time Fourier transform. So due to that reason, this STFT gives you fixed resolution kind of analysis. And motivated by that, the wavelet transform was proposed. And wavelet, actually what we do, we use scale function, and that is mother wavelet, and with the different scales we generate daughter wavelets. And these different scales provide you different kind of resolution. Like if you select low scale, it gives you good time resolution. And if you select large scale, it gives you a poor time resolution. And at low scale provide you good time resolution that is suitable for high frequency component, and large scale that provides you poor time resolution or good frequency resolution that is suitable for low frequency component. So in this way, by using different scales, we can have multi-resolution analysis of the signals. Like different parts, they require different kind of resolutions, kind of scales. That flexibility is available in the wavelet, and by using different scales, we can do multi-resolution analysis. And this wavelet transform can be implemented with the help of filter bank. So like where this you have signal, and nicely you can have low pass filter, high pass filter, and you downsample by 2. So in this way, 2 channels are there, and these 2 channels will give you approximation detail. So approximation is like low frequency part, detail is high frequency part. Again, you can decompose approximation detail, and that way we can have nice filter banks for implementation of the wavelet transform. And this filter bank also, filter bank based this wavelet representation, there are 2 issues: how to select number of levels in the discrete wavelet transform or wavelet transform decomposition, and second one is which mother wavelet should be used. So motivated by these 2 problems, 1998, this Wang and others, they proposed empirical mode decomposition. So this empirical mode decomposition method, fundamentally it is different. It is actually, it is not like a Fourier like in Fourier transform we use sinusoidal basis functions. In wavelet transform we use wavelet basis functions, and this actually this full EMD based method, it doesn't require design of basis functions. Instead of using this mathematical formula, like in case of Fourier transform, in the wavelet transform we use mathematical formula, we design basis functions and we accept coefficients, and these coefficients are the weights of the basis functions, and that we can represent the signal. On the other hand, this EMD works in different way. It doesn't use analysis formulas, it doesn't use mathematical equations, it uses an algorithm to decompose the signal. So like this signal, and there is algorithm, what it does, it determines maximas, minimas, and then interpolate maxima, minimas, and then you determine 2 envelopes, then you go for averaging of these envelopes, then we call it like average signal, then we subtract from the signal, that is residual. And residual, then we satisfy 2 conditions that we will see in coming slides, that if residual is satisfying these conditions, then we call it intrinsic mode function, IMF, because the whatever this component, whatever signal that actually we are obtaining basis functions, that is part of the signal itself. So due to that reason, these actually basis functions that we obtain from the signal, we call them intrinsic mode functions, IMFs. So in this work, we have actually EEG signals, and then these EEG signals are obtained. And this is in this work, whatever we have recorded some signals, and some signals have been obtained from publicly available databases. And once you record EEG signals or you get from the publicly available databases, then you apply EMD method, and then you can have intrinsic mode functions, IMFs. And these IMFs actually, this is one of the motivation for using this EMD method for EEG signal is like when you use Fourier transform, use Wavelet transform or other transforms, then basis functions based transform. So we represent these EEG signal in terms of basis functions. For example, like EEG signal in terms of sinusoidal functions, EEG signal we are represent in terms of wavelets. But EEG signal is not sinusoidal. EEG signal is not wavelet. And this whatever this EMD method, that actually whatever basis functions we obtain, that is part of the signal. So actually physiological it makes sense. So whatever basis functions you are obtaining here, they are part of the signal. They are actually similar to the signal. They are obtained from the signal itself. They are dependent on the signal rather than like in case of Fourier and Wavelet, these basis functions are independent of the signal. So due to the dependency of the basis functions on the signal, that is correlation between the basis function signal will be very useful for physiological interpretation of the analysis. So in that way, we have obtained intrinsic mode functions IMFs using EMD method. And then these IMFs, whatever we obtain, we have converted into analytic signal with the help of Hilbert transform. So then you have analytic IMFs. Then we obtain area feature based on the modified center tendency measure. And once you have area feature from this analytic IMFs, then we apply Kruskal-Wallis statistical test that gives you statistically a significant difference between a normal and seizure EEG signals. So normal means these persons, they never had epilepsy disease, and seizure means they have epileptic disease in the present at the moment. And another methodology, we have obtained analytic IMF, then we determine amplitude modulation and frequency modulation bandwidth features. And then these features we employ to least square support vector machine classifier. And then it classifies these EEG signals into two classes, seizure EEG signal, non-seizure EEG signal. So non-seizure means includes seizure free and normal. Seizure free means these people, earlier they were having epileptic disease, and now treatment has been done. Now they are epileptic disease, epileptic free. So they don't have seizures. So it's called seizure free. In third method, we have computed instantaneous area feature from the analytic IMFs. Then we have suggested some decision rules and which will provide you epileptic seizure detection. So for this study purpose, actually we have taken this EEG dataset, which is publicly available by University of Bonn, Germany. And this dataset includes 5 subsets, Z, O, N, F, and S. And this each like Z subset, each subset has 100 EEG signals. And Z is corresponding to eyes open, healthy subjects. And O is corresponding to eyes closed, healthy subjects. N and F, they are associated with the seizure-free subjects, and S the subset S is recorded from the seizure subjects. So in this way, this database has a recording from the normal people, seizure-free subjects, and seizure patients.
Hello. 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 Sir, your voice is not coming. Sir, you are not audible. Hello. Hello. Sir, you are not audible.
Sir, voice is not audible, sir.
Hello. Sir, you are not audible. Yes, sir, might be rejoining.
Dr. Udit?
Yes, sir.
Yes. Yes, yes. Actually it was disconnected, I think.
Yeah, your voice was not coming.
Now it is coming?
Yeah, it's coming fine now.
Okay. Are you able to see slides?
Yes.
Okay. So we have seen actually this EMD method can represent the signal, this EEG signal to set of MFM components, that is amplitude modulated and frequency modulated components. And each IMF that we obtain using EMD method satisfy two basic conditions. So these are very important conditions. Number of extrema and number of zero crossings must be the same or differ at most by 1. So this condition ensures that whatever this IMFs we obtain, that is actually similar to sine cosine function. And second condition, the mean value of the envelope defined by the local maxima, local minima is 0. So this condition ensures that whatever IMFs actually we obtain, they are symmetric in nature. So these two properties are very useful, and we will see how these two properties are useful for extraction of the features. And that I mentioned you this whatever IMFs actually we obtain in this method, they are based on the residual. So we have signal, and then we determine maximas and minimas, and based on the maxima we interpolate them, and then we have two envelopes, envelope corresponding to maxima, envelope corresponding to minima. Then we determine average of these two envelopes. So that average actually we subtract from the signal that we call residual. So in that way, we at different actually levels we determine residuals. So residual should satisfy these two conditions. If it is not satisfying, then we repeat the process, the maximum and picking up maximum minima and then subtracting it. And in that way, it goes till we get IMF. So once you get first IMF, then we subtract this first IMF from the signal, and then we whatever residual we obtain, then we do again same process. When we get another IMF, second IMF. So after once you get second IMF, then this first two IMF will be subtracted from the signal. Then whatever residual we get, then that from that we will try to get third IMF. So in this way, we extract all possible IMFs from the signal, and in the end we have residual. So from which further no IMFs can be derived. So in that way, we can represent signal with the help of these functions, these IMFs, and the last residual. So for example, in equation 1, we have capital M number of IMFs and last residual, that is M, because from that we cannot derive further IMFs. And this is the one example where we can see this empirical mode decomposition of EEG signal. So that is actually that is epileptic seizure. So that I have mentioned, when you have epileptic seizure, then this all neurons in the brain, they synchronize together and they generate very high electrical activity. And due to that, there is a presence of spikes in the EEG signal and higher amplitude. And these are the two important features that actually doctors see for the diagnosis of epilepsy. And here you can see when you are this EEG signal, when you are performing this empirical mode decomposition based analysis, then you have first IMF, second IMF, third IMF, fourth IMF, fifth, sixth, seven, eighth, and last one is the residual. And this first IMF is corresponding to the highest frequency present in the signal, and the eighth IMF is corresponding to the lowest frequency present in the signal. So this Patrick Flandrin and his team actually they have shown that first IMF, whatever we obtain, that is actually corresponding to low scale, because that is like this is the detail. And last one, 8th IMF, whatever we get, that is corresponding to approximation, and the lowest frequency component that is present in the data. So like it is also one kind of wavelet decomposition, and without designing any wavelet. You don't need to design wavelet, you don't need to select any wavelet, and you don't need to determine number of labels. So this method is automated, and if you give any signal in automated manner, it will decompose into like for example, this case up to 8th level, 8 IMFs, and residual is the time varying DC. So it's just the trend of the data. So in this way, and we can get this whatever signal actually give, it will give you decomposition in terms of oscillating components. They are narrowband in nature, and they're like sine cosine functions. So what actually we have done is, once you have these components, once IMFs, then these IMFs can be used to define the feature. And so for that, what we have done, we have obtained analytic signal representation of these IMFs. So analytic signal representation of signal ZT can be obtained with the help of Fourier transform. So for example, CT is the signal plus J times C cap T is the Fourier transform. So this CT plus J times C cap T gives you the analytic signal, that is AT to power J phi T. So it is like time varying phase. So your amplitude and the frequency, the changing with time in complex plane. So this analytic signal representation of mth IMF can be given by the equation 2, ZMT equals to AMT e to power J phi M. So AMT is the time varying amplitude and phi MT is the time varying phase. So when you say a magnitude and phase, like magnitude and phase, that is actually, that is unique representation of the complex number. So this, when you go a signal in complex plane, then you have in its unique representation. Phase actually definition, it's unique. Like generally magnitude and phase be defined for the complex signal, but when you use this phase word for real signal, then that is not unique definition of the phase. So by doing this analytic signal representation, we are able to define this phase in a unique manner. And this analytic signal representation of IMFs actually has two interesting properties. So one, the plot has direction of rotation, and the rotation in the plot has unique center. So these two properties actually, they are very useful for the defining the features, so that you can see. So here you can see EEG signal, this is analytic signal representation of EEG signal, and there is no circular symmetry. And you can see there is presence of multiple circles and multiple centers. On the other hand, if you see the analytic signal representation of IMF 1, 2, 3, 4, they have circular symmetry and unique center. That actually, which helps us to define area parameter for these analytic signal representation of IMFs, IMF 1, 2, 3, 4. And here for EEG signal, it is very difficult to define area parameter kind of thing. And area parameter is actually so simple parameter that everybody can understand. So now how to define this area parameter. For that we have to determine the radius of this area, this circular pattern. So for that we have proposed the automated actually method that is based on the center tendency measure CTM. So for this is the actually proposed approach. So if you n is the total number of points and r is the radius of the central area, then we modify CTM is given by the equation 3. So CTM actually defined as is equals to sum of n1 to capital N delta dn divided by capital N, total number of points. And delta dn actually it is 1 if it is this point is less than the radius. Otherwise it is 0. So in that way the CTM will count number of points which are falling in the specified radius. So if you are like for a given radius, you can compute the area, and in this work what we have proposed for the 95% CTM, we have selected 95% CTM to compute the radius. And once you have a radius corresponding to that CTM, that radius can be used to compute the area. So in that way this area has been computed, and this area actually we have used as a feature for analysis of normal and seizure EEG signals. So after that, based on this area, like in HTFT, we divide this signal into different segments. And here also we have proposed instantaneous area from the for the EEG signal divide. We have divided this EEG signal different segments, different windows, and then we have computed area for each window. Then interpolation of these areas gives you instantaneous area, and instantaneous area at any point is computed by using moving window method. And the selected size of each moving window is 3840 samples, and this window size is kept uniform for all EEG signals. And mathematically instantaneous area of the mth IMF is defined by the equation 4. And the third method actually we have proposed AM and FM bandwidths of analytic IMF. So in signal processing, when we talk about the bandwidth, actually it is generally spread of the signal in frequency domain. So like whatever somebody asks what is the bandwidth of the signal, so our straightforward approach is to just see the spectrum, and the spectrum is spread. What is the spectrum is spread? So this is actually the bandwidth definition. It is based on the Fourier Transform, Fourier spectrum, that is stationary signal processing. But 1990, this Cohen and Lee, they come up with new definition of AMF bandwidth. That is very interesting bandwidth. And when we did this work, actually there was no paper which used these bandwidth parameters for any application. So our group was the first one. They actually explored this concept, bandwidth concept, for this application, this epileptic seizure classification. But there is a lot of scope actually. What is the beauty of this bandwidth definition? Like it is not based, the whatever spread we have in frequency domain, it depends on the variation in time and frequency. So it depends on the amplitude modulation and frequency modulation present in the signal. And whatever signals in real life we have, they are wideband signals. So when you compute this bandwidth, like whatever expressions mentioned in the equation 5, you need to have monocomponent AM/FM signal. So like this signal should have only single tone kind of nature. It's all like one sinusoidal, and its amplitude and frequencies, they are allowed to vary. So here, how to get monocomponent AM/FM signal in real life, it is very difficult. And this empirical mode decomposition, it is such a platform where you give any wideband signal, it will give you the set of intrinsic mode functions IMFs, and that these IMFs can be considered as a AMF set of AM/FM components. And once you have AM/FM component, then you can apply these bandwidth formulas, like bandwidth due to amplitude modulation depends on the time varying amplitude, and bandwidth due to frequency modulation depends on the time varying phase or frequency, instantaneous frequency. So in that way, both this bandwidth can be computed using this EMD method. And now we will see some results first we'll go for analysis of normal and seizure EEG signals. So this subset S, subset Z from the database form the normal class, and subset S from the seizure class. And this method can detect patients with epilepsy using EEG signals from normal people. And EMT based decomposition helps us to cover more than 95% of the data points which lie within the circle due to having circular form of the analytic IMFs. And this area parameters that have been estimated for both the classes, normal and seizure, based on the analytic signal representation of IMFs of various window lengths or sizes like 500 samples, 1000 samples, 2000 samples, and 4000 samples. So this is very nice plot that you can see. This is a CTM, a plot of CTM in terms of percentage versus radius. So here you can see for normal case, the requirement of radius is actually very less. Like it is up to 250 or around 300. Radius can cover CTM up to 100%. On the other hand, if you see seizure, in case of seizure, variability is very high. So this requirement of radius, in order to have 100% the CTM, it goes up to 1000 or more than 1000. So there is actually a radius requirement is different. In order, for example, if you fix 95% CTM, then requirement of radius will be very high as compared to the for the seizure as compared to the normal case. So this motivated us to use this radius as a feature, and initial radius we have computed this area based on the circular symmetry. So that area is such a simple feature that can be connected with the epileptic seizure detection. And these are some results. We have compared normal and seizure free these classes based on this area parameter when window length is 4000 samples. For the first 4 IMF. So because this database is only 4 IMF, is the common number of IMFs in all EEG signals. So based on that, we selected first 4 IMFs. And here you can see this Kruskal-Weiss statistical test outcome is probability. And the probability value is coming 0.05 or less than 0.05%. Then we call it a statistically significant difference. And here you can see this Kruskal-Weiss statistical test is providing a statistically significant difference between normal and seizure classes using area parameter. Then same study we have done for the window length 2048 samples, and here also we can see this area parameter is able to discriminate seizure and normal classes with a statistical significance. And because here in this case also probability values are 0 for all first 4 IMFs. And same thing actually we have observed for the window length 2000 samples. Here you can see nicely this area parameter for seizure, it is higher compared to the normal, and it is able to discriminate this first 4 IMF. They are able to discriminate seizure and normal classes with a statistical significance. And same thing for 1000 samples length of this data for normal epileptic seizures and classes, and you can see in this case also we are having statistically significant difference that is clear from the Kruskal-Weiss statistical test because probability values are 0. And for 500 samples length also we can see this first 4 IMF they are able to provide a statistically significant difference between normal and seizure classes. And this actually one of the important because why we are studying this segment like the size of the window that is for different methods for analysis. And because if you are able to get the better analysis performance, better classification between the seizure and normal using this area parameter with the smallest window size, then that is very good for implementation point of view. Your method is suitable for real-time implementation for the diagnosis purpose. And on the other hand, it is also useful for the subject. The subject doesn't need to wait. You don't need to record data for a long time. So in both point of view, it is important. So that is why in biomedical signal processing by healthcare, we want our algorithm should implement in the as small as data. So that has many advantages. And in this table, you can see the area of analytic signal representative of IMFs for the normal and seizure subjects for different window size, 500, 1000, 2000, 4000 samples. And these are IMF 1, 2, 3, 4. And you can see minimum, maximum, and median values of this area parameter. And from this table, it is clear that for the seizure, the requirement of area is higher as compared to the normal. And then actually in literature, there are various methods. They have used signal processing and machine learning algorithms for the automated classification of normal and seizure EEG signals. So like Nigam and others 2004, they use nonlinear pre-processing filter, diagnostic artificial neural network, and they got 97.2% classification accuracy. And then the Srinivasan and others 2005, they got time and frequency domain features. Together with recurrent neural network, they got 99.6% classification accuracy. Kanathar and others 2005, they used entropy measures, adaptive neurophagy inference system, ANFIS, and they got 92.22%. And Polath and others 2006, they used fast Fourier transform and decision tree. They got 98.22% classification accuracy. And Sovasi 2007, they used discrete wavelet transform, mixture of expert model, and they got 95% classification accuracy. And this proposed method, we have not used any machine learning algorithm. So based on the simple linear threshold, this area measure that provides you 100% classification accuracy. So selection of the spoon depends on the type of food. Suppose you want to have noodles, then use fork because your food is discontinuous and spoon is discontinuous. So discontinuous food can be handled with the nice discontinuous spoon. So similarly here, the signal analysis technique depends on the nature of the signal, and the signal is actually nonlinear, non-stationary. And luckily, we have also got similar kind of signal analysis technique, and in that way, nicely this decomposition was performed, and we got very good parameter linked with the seizure activity. So it was nicely discriminating with the good accuracy, and so that here without classified like simple linear threshold can be used to implement this algorithm for perfect separation between normal and seizure classes for this database. And after that, now we will see the classification of seizure and non-seizure EEG signals. So for this actually subset Z, O, N, and F, they are combined to form the non-seizure class, and subset S form the seizure class. And this methodology can detect patients which have epilepsy from the normal and seizure-free persons. And EMT method can decompose nonlinear non-stationary EEG signal into set of narrowband AMFM components or IMFs, and which help us to compute bandwidth due to amplitude modulation and bandwidth due to frequency modulation. And this bandwidth features whatever this we compute, it also tells us what is the contribution due to amplitude modulation and what is the contribution due to frequency modulation component. For example, if you don't have AM component in the signal, then bandwidth due to only frequency modulation. Similarly, if you don't have frequency modulation component in the signal, then bandwidth will be due to amplitude modulation. And we don't have both, then there will be no bandwidth will be 0. So in that actually, this is it can tell us the contribution of different parts. That is a very useful physiological interpretation of the data. And now we will see some results. This is bandwidth to amplitude modulation for the 8 IMFs, and here you can see for seizure and non-seizure EEG signals. And the first 4 IMFs, the bandwidth due to amplitude modulation is able to show the difference. For the remaining IMFs 5 to 8, these actually bandwidth due to amplitude modulation, they are not able to show the difference. They are overlapping to each other. And the same thing we will see to bandwidth due to frequency modulation here. And bandwidth due to frequency modulation, that is actually able to show the difference between seizure and non-seizure EEG signals. On the other hand, this first 4 IMFs, is it audible? Dr. Udit?
Now it's audible. In between, there was some glitch.
Oh.
Yeah. It's fine, sir. It was just for a second, few seconds.
Okay, okay. So this bandwidth due to frequency modulation. Thank you very much. Thank you. Yeah, bandwidth due to frequency modulation. Here you can see the first four IMFs. This it is showing the difference, and the remaining IMF 5 to 8 IMFs, they are not able to show the difference between the seizure and non-seizure classes of EEG signals. And that is also actually clear from the probability value of these bandwidth features. So here you can see this probability value for the bandwidth due to amplitude modulation, bandwidth due to frequency modulation features. So first for IMFs, this probability value is less than 0.05, and other case this is not less than 0.05. So due to this reason, we have selected this first four IMFs for classification purpose. And here you can see in this case we are not getting perfect separation like non-seizure case. Here we actually, so that motivated us to use classifier for the separation of these two classes. So we have used this 4 IMFs for the classification purpose, and this classification has been carried out using least square support vector machine classifier with the help of amplitude modulation and frequency modulation bandwidth parameters. So least square support vector machine classifier, that is actually that's an improved version of the support vector machine. And here for two class support vector machine, we consider the following decision function. That is in equation 6, we can see fx equal to sine wtgx plus b. And here w is the L dimensional weight vector, gx is the mapping function, and b is the bias. And based on the sign, we can take decision. If sign is coming plus, then we say this is one class, and sign is coming minus, then we say this is second class. And this is the basic structure, basic block diagram of the SPM, least square support vector machine classifier. So we like bandwidth due to amplitude modulation and bandwidth due to frequency modulation, these bandwidth features. Some of the bandwidth features we have used for training set, and we perform the training to least square support vector machine classifier with the help of kernel function and its parameters. And then once you train this LSSBM classifier, then we use the remaining remaining bandwidth features for testing purpose. And during testing, based on this sign parameter, whether output is 1 or -1, we take decision whether it is seizure or non-seizure class of EEG signal. So we will see now here actually the following kernel functions have been used for the study purpose, like polynomial kernel, which is described in equation 7, and where L is the degree of polynomial. And similarly, radial basis function that is also used for this study, that is shown by the equation 8. And here sigma controls the width of the RBF kernel. That is so this is important parameter. And then we have used Mexican head wavelet kernel function, which is defined by the equation 9, and Morlet wavelet kernel function is defined by the equation 10. So after that, in order to measure the performance of the classifier, we have used this performance measures: sensitivity, specificity, and accuracy. Sensitivity, it is the proportion of epileptic seizures which correctly detected by the algorithm, and mathematically it is represented by TP upon TP plus Fn, 200. And specificity is the proportion of the segments without seizures and correctly identified by the algorithm, and that is Tn upon Tn plus Fp. Similarly, accuracy, it is the proportion of the correctly detected seizures and non-seizures by the algorithm, and that is given by the Tp plus Tn upon Tp plus Tn plus Fp plus Fn. So in that way, these three performance measures have been computed, and this is actually a table which shows the results like sensitivity, specificity, and accuracy of IMFs with different kernels of the LSSM classifier for the classification between non-seizure and seizure EEG signals. So this kernel function, that is polynomial, RBF, Mexican head, Morlet, and these are the kernel parameters which we obtain based on the trial and error method. And one can go for actually more optimum, more robust approach to select these parameters. And then statistical parameters, sensitivity, specificity, and accuracy, that has been obtained, and these are the results for IMF1, IMF2, IMF3, IMF4, and minimum value of this. So this tenfold cross validation has been proposed, has been studied, and based on the out of 10 different band combinations. So the minimum accuracy out of 10, and that is the maximum accuracy out of 10 for the various IMFs. And you can see the second IMF is able to show the difference, able to show the better performance as compared to the other IMFs with the Wavelet kernel function and with this parameter set. And here you can see this for the Wavelet kernel for second IMF. Then we have also validated with the another performance measure, that is receiver operating characteristics, and we generally use area under ROC, that is area of the receiver operating characteristics curve, as a performance measure. So if it is approaching to 1, then we call it better classification performance, otherwise it is not better. So here you can see this ROC plot, that is the plot of the sensitivity versus 1 minus specificity. And we have studied various kernel function, polynomial, RBF, Mexican AT, and Wavelet. And for Wavelet case, area under curve equals to 1. That is actually, so this is also validated that Wavelet kernel function is giving better performance. That is also evident with the help of area under ROC curve. And this is very important, actually, important result. That is bandwidth, that bandwidth parameter that we have used as a like feature set. So this is the training phase. After training, this is the boundaries that actually have been obtained using SBM, this Wavelet kernel function. And now here you can use this as a computer-aided diagnosis tool. So for example, like if you are in a rural area where you can record EEG signals, and from the EEG signal we can apply this EMD method, and you can detect second IMF. You can select second IMF. On the second IMF, we determine bandwidth due to amplitude modulation and bandwidth due to frequency modulation. And these two bandwidth actually you can map here in this space, in this plane. And if these two bandwidth feature they are mapping here in the this area, like dashed area, then we call it it is a seizure, otherwise it is non-seizure. So in that way, this automated identification of the disease can be performed. And this can be performed by the smartphones or mobile. And the smartphone, if it is able to detect epilepsy using EEG signals with this kind of a tool, and it really is smart. So that is one of the actually lot of interest these days. People want to use the smartphones or mobiles for the diagnosis purpose, for the healthcare, because everybody is carrying mobile, and everybody is having the smartphones. So these algorithms actually can be implemented in this such platform, and this mobile is always with us, so that this detection of the disease can be carried out at the initial level. So because always you are checking, always you are estimating these parameters, always you are evaluating your health, and that health can be assessed in real-time manner with such kind of tools. And this is also such kind of actually study is also known as computer-aided medical diagnosis, and that is actually one of the highly studied topic these days because a lot of interest and a lot of useful applications. So then we have compared our method with the other existing methods in the literature for seizure and non-seizure classification. So Tajlas and 10.7, they use time frequency analysis and artificial neural network, and they got 97.73% classification accuracy. OCAC in 2008, they use approximate entropy and discrete wavelet transform genetic algorithm. They got 96.15% classification accuracy. Liang and 2010, they use time frequency and approximate entropy analysis, linear nonlinear classifiers. Then they got 97.82 to 98.51% classification accuracy. Ling and others 2011, they use multi-wavelet transform and approximate entropy feature with multi-layer perceptron neural network, and they got 98.27% classification accuracy. And proposed method actually that use empirical mode decomposition and bandwidth features together with least square support vector machine classifier, that gives you 99.5 to 100% classification accuracy. And that is actually that you can see this. There is a lot of actually 10 people are using signal processing, machine learning, and this alone machine learning is not so efficient, and that Dr. Udit has selected a very nice topic for this faculty development program, that is combination of both signal processing machine learning algorithms. So that actually in my next talk that I will cover the various parts, like even people are applying deep learning, alone machine learning, that is not suitable. When you go for combination, that is more suitable and more useful for interpretation. So signal processing actually is an important part for the when you are dealing with the signals, and not just for, because like health, like assessment based on the biomedical signals, based on the physiological signals, then you have interpretation is also important. And when you have features, then you have nice interpretation. So here you can see this proposed method is actually based on the features, and based on the NB features are extracted based on the signal processing, and together machine learning algorithm we get good classification performance, and that is better than the other existing methods. And after that we have actually proposed method for epileptic seizure detection algorithm. That is very important problem, and people want to detect epileptic seizure in real-time manner, and there are a lot of actually research is going on, and they want to have detect that seizure, and then you can have the required medicine. So for example, somebody is driving a car, and that person is going to have epilepsy attack, and such algorithms, whatever the epileptic seizure detection algorithm, they can detect this attack, and once it detected, then you can make alarm, and you can warn that person, and he can stop the car, he or she can stop the car, and he can take the required medicine, that epilepsy drugs are there, and then this attack can be bypassed. So this, due to this reason, epileptic seizure detection are very important, and especially for long data recording. So like for example, somebody has epileptic seizure attacks, is admitted in ICU. Such algorithms can tell you how many times that person has attack. So because detection can be done on that times. And once you detect the seizures, then this method can help to provide immediate required treatment for the epileptic patients. And for this, actually in this work, we have computed instantaneous area parameter from the windowed analytic IMFs of EEG signals, which provides rule-based detection of the epileptic seizures. And for that purpose, we have used publicly available database, that is by University of Freiburg, Germany, which has been used in this work. And that is for focal epilepsy. So this data set actually includes invasive EEG recording. There are two types of recording. One is recorded from the outside surface, that is surface electrodes, that is non-invasive EEG signals. And sometimes when you have focal epilepsy, and then actually and you have to go for some surgery and some operation kind of thing, then these signals are recorded from the inside. They are known as invasive EEG. And this actually, this focal epilepsy case, in 80% cases, there's a drug-resistant epilepsy. So there's medicines that doesn't show any effect, and you have to go for operation, surgery. And that is why this, once you go for surgery and you remove that area, because that area is fixed in the brain, and from there, the seizures are always originated. So in order to remove that area, you have to identify that particular area accurately. And for that, machine learning and signal processing algorithm, they play important role. And so in this work, we have used this EEG recording of 21 patients. And this EEG data have been acquired using digital video EEG system with 128 channels and with the sampling rate of 256 Hertz. And analog to digital converter, the 16 bits has been used. And so we have 3 intra-source reports of 9 patients with focal epilepsy, which is originated from the temporal lobe region. And total, we have 90 segments in this study for each channel, and 51 of them without epileptic seizures, and 39 segments not having only one epileptic seizure. And here you can see this is the signal, actually EEG signal, and which has one epileptic episode in the middle. And that is not so much clear. But when you perform decomposition using EMT method, then this is the first IMF, second IMF, third IMF, and second and third IMF, you can see this booster. You can see nicely presence of epileptic episode in the middle. And then when you have computed instantaneous area of these first, second, third IMFs, there this is a EEG signal, and there is a nice boost up, and you can clearly see the onset and offset of the this epileptic episode. And this dashed line, whatever you see here, they are actually suggested by the neurologist and the other references. And this circles, whatever in the beginning and ending of this episode you see, that is by our proposed method. So you can see this whatever actually we have detected this episode, that is validated by the neurologist's opinion, neurologist as a reference. And here also you can see that epileptic seizure actually becomes severe in the middle, but we can detect in the beginning itself, initial level. So that helps us to actually detect this epilepsy attack in the advance, and required medicine can be given to that person so that attack can be bypassed. So it's very around and the patient around 10 minutes before, 5 to 10 minutes before, you can detect it, and then required medicines can be given, and that way attack can be bypassed. So this method is actually based on the 3 channels and 3 IMFs. So we have also suggested some decision rules for the epileptic seizure detection, which is based on the instantaneous area of IMFs has been performed by the help of following decision rules. The first decision rule requires the computation of threshold of the instantaneous area of IMFs of EEG signals for all channels, and the threshold of mth IMF is computed by the equation 11. And this equation actually we have derived empirically. And the second decision rule requires identification of those seizure activities which are available in at least 2 of the 3 instantaneous areas of IMFs of each channel. And third rule requires making an interchannel decision based on the identification of those seizure activities which are available in at least 2 of the 3 channels, where presence of seizure activity in each channel is decided by the rule 2. So in this way, based on the majority, we take the decision in favor of the seizure or seizure free. And these are the results, performance evaluation parameters for the different patients, and segments, and true positive, true negative, false positive, false negative. And this is obtained sensitivity, specificity, positive predictive value, negative predictive value, error rate detection. And sensitivity, specificity already we have defined earlier. And this PPV and PBARD, they are defined by this bottom and this right. And here you can see for this study, this sensitivity, specificity, PPV and PB, they are expected to be high, and they are having high values also. ERD is expected to be less, and it is less also. So in this way, our proposed method for epileptic seizure detection is actually providing the desired results. And then we have compared this study with the epileptic seizure detection method, which are studied on the same database. And Orozco and others 2009, they use energy of IMFs of EEG signals, and they got various sensitivity, specificity, PPV and PVRD values. And Correa and others 2009, they use energy of EEG signals, and they have got these actually table, these values are shown in table, performance measures. And our proposed method, that is based on the instantaneous area measure of analytic IMFs of EEG signals, which shows the better performance than the other existing methods. And ERD should be less, and this is giving less ERDs compared to the other 2 methods. Sensitivity, specificity, PPB and PB, these parameters should be high, and you can see they are coming higher also. So in that way, better performance can be obtained with the proposed method as compared to the other existing methods. And after that, we have actually applied this time frequency image based concept for the classification of sleep stages, and that is actually a very useful concept. And these days people are trying to use deep learning, convolutional neural network concepts, and for one-dimensional signal. And how to do that? So time frequency distribution gives you an opportunity where this one-dimensional signal can be two-dimensional image. Directly this time frequency image of the one-dimensional signal can be used with the CNN, this convolutional neural network classifiers. So these EEG signals are commonly used signals for the classification of sleep stages. And sleep stages classification actually is a multi-class classification problem, and it is very useful for the diagnosis of sleep disorders. And the very old method, it was proposed in 1964, around 1964, that is known as RNK standard. And according to RNK standard, the sleep stages actually, there are 6 sleep stages when you sleep. That is awake and non-rapid eye movement S1, S2, S3, S4, and rapid eye movement. So this rapid eye movement REM, this is very important actually stage, and this is responsible for the dreams. So like whatever dreams, and some this rapid eye movement, that is also corresponding to the Brahma Muhurta that we call in India, like morning time, 3 o'clock to 5 o'clock. This time is Brahma Muhurta, and rapid eye movement takes place around in the end, like 5 o'clock, 4 to 5 o'clock. So this actually, this is also responsible for the dreams, like in villages. Sometimes if you have seen dreams and you share this to your family members, then family members will ask you what time you have seen this dream. So if you say that I have seen this dream in the morning time, then people will take it seriously. And if you say that you have seen this dream in the night time, then okay, it may be. So when you see the rapid eye movement cycle and morning time, then it makes sense. So it is deep sleeping. And also there is a lot of interpretation. There is a lot of research is going on to understand the dreams. So various, like when you see the monkey in the dream, then what is the EEG signal? When you see the some good sweets in the dream, then what is the EEG signal? When you see the elephant, then what is the EEG signal? So different actually objects and what is the EEG signal. So then people want to understand dreams with the help of dictionary. So they are designing various dictionaries for different objects, their corresponding EEG signals, and then based on the matching, they will tell you in the daytime what dreams you have seen. So there is a lot of actually in India also, like a lot of interpretation in the villages. If some girl has seen the bangles in the dream, then in rural areas, people, they interpret that this girl is going to get married this year. So there's a good news for entire village, and they say some good function will take place. So people will be happy. So in that way, this actually people interpret dreams in different ways. And very other actually very an important thing is that alcoholic people, they cannot see dreams. And in the research, actually, it has been shown they don't cover rapid eye movement stage. They have only 5 stages instead of 6 stages. So their sleep cycle is incomplete. So they don't go for rapid eye movement that is responsible for the dreams. So these alcoholic people, they don't see the dreams. That is actually, so indirectly they accumulate the depression, they accumulate the sleep disorders. And recently, American Academy of Sleep Medicine, ASM, actually, which combines sleep stages S3 and S4 of RNK sleep standard into single stage, which is known as slow wave sleep. And now this RNK standard, we have 6 sleep stages, and American Academy of Sleep Medicine, we have 5 stages. And the classification of these sleep stages is actually very tough, it's a challenging task due to inter and intrascale variability. So the doctors, what they use manual sleep scoring method to separate them, to classify them. So there is actually there is strong motivation for using signal processing machine learning algorithms to classify these multiple classes for the sleep stage. Dr. Udit?
Yes, sir.
Yeah, is it audible?
Yes, it's audible.
Okay, thank you very much. Thank you. So this is the proposed methodology as a block diagram of proposed methodology. So we have EEG signals of sleep stages, awake, non-rapid eye movement, S1, S2, S3, S4, and last one is rapid eye movements. Total are 6 sleep stages in according to RNK standard, and these will be 5 according to American Academy of Sleep Medicine. So from the EEG signals, we obtain time frequency representation based on the pseudo-Wigner-Wille distribution method. So actually, Wigner-Wille distribution is one of the classical classical techniques for obtaining time frequency representation, but it suffers from cross terms problem. So there's improved version of Wigner-Wille distribution is pseudo-Wigner-Wille distribution. That is smooth pseudo-Wigner-Wille distribution, doesn't have cross terms problem as compared to the Wigner distribution method. So due to that we have used here pseudo Wigner-Wille distribution method for obtaining time frequency representation. This time frequency representation shows the energy of the signal as a function of time and frequency. So this energy is actually positive quantity. So in order to represent this, we can actually go for image because intensity is also positive. So this energy can be converted into intensity of the image. So this time frequency distribution can be converted in the form of time frequency image. Then we have performed segmentation of time frequency image of EEG signals based on the frequency bands of rhythms. And then features based on the histogram of sub-images of the signals can be obtained, and then we can give these features as an input to multi-class least square support vector machine classifier, and then we get awake S1, S2, S3, S4, and S5 RAM stages according to RNK standard. And according to American Academy of Sleep Medicine, we can have 5 sleep stages separation. And this is actually we have studied for EEG signal, and you can apply such kind of concepts for ECG signals, heart sounds. There nobody has studied such kind of concepts. So for this study purpose, we have used the dataset which is publicly available by the PhysioNet for sleep stages, and the recording in this database recordings have been obtained from 8 males and females whose age vary from 21 to 35 years without any medication. And the recording includes horizontal the EEG signals FPZ, CZ, PZ, each sample at 100 Hz, and according to RNK standard, these EEG signals had been segmented into different stages, and these EEG signal that we recorded from night to 12 o'clock to 5 o'clock in the morning. So 5 hours time is sufficient to include these 6 sleep stages. So based on the RNK standard, this segmentation has been carried out. And this is this figure shows the smooth pseudo Wigner-Wille distribution of the EEG signal corresponding to REM's stage, rapid eye movement. And the mathematical expression for smooth pseudo Wigner-Wille distribution is given by the equation 11. And based on that, you can get time frequency representation. And here this energy is plotted as a function of time and frequency together. And then we can convert this time frequency distribution, time frequency analysis into image representation. So this is the time frequency image of the previous time frequency distribution of the this smooth pseudo Wigner-Wille distribution of RAM sleep stage of EEG signal. And then we have performed segmentation of the gray and binary sub images. So here gray for the different rhythms like a delta rhythm, theta rhythm, alpha and beta and gamma rhythms. We have segmented this different frequency bands for gray image and for the binary image. Then we have obtained histogram of gray and binary sub images of time frequency image corresponding to frequency bands of delta rhythm, theta rhythm, alpha, beta and gamma rhythms. And after that, we have actually extracted features based on the histogram of sub images of the EEG signal. That is maximum count of pixel intensity, the histogram of gray sub images. Mathematically, it is shown by the equation 12. And is spread in the histogram of gray sub images shown by the equation 13. And aspect ratio in the spectrogram, histogram or binary sub images defined by the equation 14. And then we have used these features for multi-class least square support vector machine classifier. And here actually this decision function multi-class least square support vector machine classifier defined by the equation 15. So here, like earlier case, we are having 2-class classification problem, and here we have multi-class classification problem. So that we have used support by least square vector machine classifier. And now in this case, we require multiple kernels because classes are multiple. So for that, radial basis function for multiple class like kth class, it is defined by the equation 16. And for the Mexican head wavelet kernel function is defined by the equation 17. And Morlet wavelet kernel function is defined by the equation 18. And this is actually, these are the experiment results. And actually, what is the motivation for segmentation of time frequency image? So what we did, we also the results performance without segmentation and with segmentation. So without segmentation, we have studied various kernel functions and parameters. And these parameters have been obtained by the trial and error method. And for awake, S1, S2, S3, S4 and RAM sleep stages. And we have obtained individual classification accuracy and total accuracy, also average accuracy. So here you can see without segmentation, for example, this Morlet wavelet kernel function that provides you 79.99% classification accuracy, total accuracy. On the other hand, when you do with segmentation of time frequency image in terms of rhythms, then you can see this is with the Morlet wavelet kernel function, it is coming 92.93% total accuracy. So there is significant improvement from 79.99% to 92.93% when you use Morlet wavelet. So this motivated us to use segmentation of the time frequency image with respect to frequency bands of these rhythms. And this is the confusion matrix for classification accuracy of the sleep stages of EEG signals for Morlet wavelet kernel with window size of 64 samples. And then we have also compared our methods in the literature. So this is the RNK standard method. So this is Doros and Cobb in 2007, they use FFT based feature error Markov model. And Burrell and others 2010, they use hybrid feature and cluster based classifier using PCA. And they got total accuracy that is 61.08% and 69.98%, and that is very less. And our proposed method, which is based on the time frequency image based features and multi-class square support vector machine classifier, that provided 88.47% classification accuracy total. So it is significantly higher than the other existing methods. And still there is a lot of lot of opportunities, lot of chances to improve it. So a lot of research work can be done on the sleep stages. Less work has been done in this area, especially American Academy of Sleep Medicine. There is very less work has been reported, and it is that time only one reference was available, Su and others 2013. They use energy based features and Lehman neural classifier, and they got 87.20% accuracy for the American Academy of Sleep Medicine standard. And our proposed method actually provided 92.93% for ASM. So this shows the better results than the other existing methods in the literature. So these methods actually can be improved. And in the last part of our work, actually we have applied this multi-wavelet transform based features for human emotion classification. And that is actually one of the important this emotions are such a thing that may actually differ us from the animals, like various animals, they don't have emotions even. So this is one of the important feature of a person, that we can be happy, and it's one of the important actually feature of a person, that if you are happy, then it is one of the richest thing that a person can do. So these EEG signals actually include very valuable information related to different emotional states, and which help us to understand physiology and psychology of the human brain. And if you have any like depression, you have any like anxiety, you have stress, and if you go to doctor, and quickly they will take your EEG signal. They will record your EEG signal, and they will try to understand what is going on. And recently you can see this due to COVID-19, there's a lot of stress in the people, and that this is COVID-19 is affecting the mental health. And there is a lot of scope now. People are studying actually EEG signals and ECG signals, phonocardiogram signal, lung sounds. So there is a lot of scope, this biomedical actually area, biomedical signal processing, and that is the actually it's a requirement of time. And now a lot of people are getting a lot of stress due to this COVID-19, and the people are measuring it with the help of EEG signals. So these emotions which we measure using EEG signals are very useful, and they have many advantages as compared with other methods. For example, like many methods, they use face recognition method for emotion detection, and face can be modified, and so it is misleading. Similarly, speech signal based emotion also, people can change the way of style of speaking. So these actually the emotions, whatever we detect based on the face and speech, they can be modified. So they are not actually reliable. And whatever emotions we measure using EEG signal, they are measured from the brain activities. Nobody can change brain. Actually, brain can't change anything. So this is like inside of the brain, and they are directly coming from the inside. And sometimes the person appears to be happy to outside world, but he's not happy. and that actual happy emotion, other emotions can be detected with the EEG signals. And so due to these reasons, we have used the EEG signals for measuring the emotions. And this emotion classification based on the EEG signal can help us to develop and improve brain-computer interface system. So like the person, for example, like you are driving a car, and you can develop a automated mood detector. And like according to your mood, songs can be played in the car. So you are happy, then happy songs will be played. You are sad, then sad songs will be played. And you are depression, the depression songs will be played. So according to your mood, automatically these songs can be played. So this is actually automatically your mood can be identified. Even like it is very useful for the behavior analysis. Like you are coming from your workplace to your home, and these algorithms can detect your emotion. And according like people in the family, all members will know that you are happy, and accordingly they will behave with you. So this is very good for actually to understanding the persons, what is going on inside the brain, and that what is the mood, what kind of mood today person has, that can be detected with the help of such algorithms. And they're very useful for brain computer interfacing BCI. And like suppose somebody disabled person, newborn child, they cannot speak what they are feeling, but you can record them, you can record their EEG signal. Based on the EEG signals, you can study what is going on inside. So like if you want to, they are not feeling well, and then you can record EEG signals, and based on the signals, you can detect this person is not happy. And you perform the treatment, and the effect of the treatment can be assessed with the help of such EEG signals. And then you can find out whether a person is happy. So this means treatment is showing effects. In this way, it can help us to connect with the disabled people, that is a BCI, brain computer interfacing. And brain's BCI system can be used for assisting the physically disabled people to interact with the real world. So this is the proposed methodology. First we have experimental setup, then we apply pre-processing, then we apply multi-wavelet transform, and then Euclidean distance based features from three-dimensional phase space reconstruction that we obtain from subbands. Then we apply multi-class T-shift square support vector machine classifier, and in this work it can detect these four kind of emotions like happy, neutral, sadness, and fear. And these EEG signals have been collected from 8 healthy subjects, which include 4 males and 4 females, whose age vary from 20 to 35 years during audio-video stimulus. And the literature actually, in some papers, some studies only emotions have been studied for female subjects. And for some female-male both. And it has been shown in the literature, these females are actually, they are more sensitive, more, they exhibit significant emotions as compared to the male subjects. And but for female also there is some age, like for example 35 years, after that they also behaves like males in terms of emotions. So in this work actually we have studied emotions for both subjects, males and females, and these subjects are undergraduate students or employees from IIT Indore, India. And 16-channel EEG module, this BioPAC system in compliance to the international 10 to 20 system, has been used for the recording of EEG signals, and the sampling rate was 1000 Hertz for the EEG signals with bipolar montage for this study. And this study has examined 4 emotional states, which includes happy, neutral, sadness, and fear. And this experiment, 3 audio-video stimulus with 5 trials for each emotion from 8 subjects with F3, F4 channel of EEG signals have been used. And total 480 EEG signals have been studied with 2-second duration. So this is the actually electrode system, and where you can see the location of different electrodes for the recording. And this is arousal valence diagram, where these studied emotions, fear, happy, sad, and neutral, they have been located. And this is the complete actually block diagram of the proposed methodology. So we have this videos, this person is actually watching video, and press the video, these emotions are introduced in the person, and these emotions they have been recorded with the help of this EEG recording system. And then in computer we have EEG signal, then it has some noise, eye blinking, artifacts. Then this by pre-processing we can remove these undesired parts of the signal, and then we apply non-stressing signal decomposition methods, and that will you decompose this complicated signal in terms of simple signals. Then we extract features And these features is given as input to multi-class classification that is done by least square support vector machine classifier for multi-class cases. And this multi-wavelet actually is an extension of the idea of a scalar wavelet, where multiple scaling functions and associated multi-wavelets are used, each of single one. So instead of a single mother, one mother, they have many mother wavelets. The multi-wavelet offers the advantages like simultaneously exhibit orthogonality, short support, symmetry, and second order approximation. The commonly used multi-wavelets are employed in our work. They are Garno-Yumo, Hardin, Mesopusser, that's a GHM, and Chuilian, CL, and SA4. These are three commonly GHM, CL, SA4 multi-wavelet that we have explored. And the three-dimensional phase space reconstruction that actually we have used. So this phase space representation and concept of phase space representation is an important tool for characterization of the high dimensional dynamic systems. So in order to extract the nonlinear dynamics of the sub-signals, which we obtain using multi-wavelet decomposition, we have used phase space reconstructions. And phase space reconstruction of the subband signals can be expressed by mathematical expression. And here is the example of the third level subband decomposition. Third level, then you will have one approximation and three details. So these are three level decomposition. So we have four subbands and we have three-dimensional phase space representation of these four subbands. And now how to quantify this variability that is present in the three-dimensional phase space representation. So that we have used mean of equivalent distance and standard deviation of equivalent distance as a features for this three-dimensional PSR, and then this is based on the Euclidean distance actually. So recently we have extended this three-dimensional. Now actually recently we have studied up to 10-12 dimensions, and we have found that like 8 dimensions, 9 dimensions when you go for PSR, that can able to separate actually more, that can provide more separability of the classes. And from this, once you go higher dimension, then based on the Euclidean distance concept, you can come back again to one dimensional signal. So this is actually very interesting bridging between the signal. You can, for example, you have EEG signal, then you go to three-dimensional PSR, and from that you can come back again in one-dimensional PSR. So one-dimensional Euclidean distance, and from the one-dimensional Euclidean distance, you can extract features. So in that way, you can study the various number of dimensions, 2, 3, 4, 5, 10, 12, up to 100 also. And based on the Euclid distance, again from 100, you can come back. So that actually, it has been observed that the higher dimensions data is well separated. And that way, so that we have observed in our recent study. So these are the experimental results. We have used GHM, CL, for multi-wavelets for obtaining third level decomposition of subsignals of EEG signals. Then phase space representation of subsignals is obtained. That is very useful for obtaining high dimensional space. And then we have obtained equivalent distance from the high dimension to one dimensional, and the mean and standard deviation of equivalent distance summarizes the complexity of the decomposed signals, which is linked with the different emotional states of the brain. And then we have given these features as input to machine learning based multi-class square support vector machine classifier with RBF, Mexican hat, and Multi-Wavelet kernel functions. And this is the table which shows the results. So different multi-wavelets, GHM, SA4, CL, and this kernel functions and parameters, RBF, Mexican hat, Multi, and these are the parameters selected based on trial and error. And for happy, neutral, sad, and fear emotions, these are the obtained classification accuracies. And total accuracies are also in the last column of the table. And you can see CL multi-wavelet together with Multi-Wavelet kernel provides you better classification for the emotions, that is 91.04% classification accuracy. And this is the confusion matrix of Multi-Wavelet kernel function of the multi-class square support vector machine classifier for classification of emotions from EEG signals with CL multi-wavelets. Then we have actually compared our proposed method with other existing methods in the literature. So Ling and others 2010, they use music of 30 seconds, and they got from the 24 channels, they extracted feature was short time Fourier transform, that was time frequency analysis technique. And they use KNN classifier, LD classifier, and they got 82.29% classifier accuracy, the 4 classes that we have studied. And Bang and others 2010, they use video of 4 seconds from the 62 channels. Minimum redundancy, maximum relevance, this method, they together with support vector machine classifier, they got 66.5% classification accuracy for the 4 classes. And proposed method, that is based on the audio video stimulus of 2 seconds, and that is from the 1 channel, that multi-wavelet transform method has been used for decomposition. And it provides, together with multi-class square support vector machine classifier, it provides 91.04% classification accuracy for the 4 classes. So this is the overview of this entire talk. From the area on the bandwidth features, the bandwidth due to amplitude modulation and bandwidth due to frequency modulation of the IMFs of EEG signals can be used as a feature set in order to classify seizure and non-seizure EEG signals. And we have seen that Modulate wavelet kernel has provided better classification performance with the second IMF and for the seizure and non-seizure EEG signals. And specific system for detection of epileptic seizures from EEG signals, and the straightness obtained by using moving window of a smallest size on analytic IMFs can provide good detection performance for rule-based detection of epileptic seizures from EEG signals. And time frequency image representation is possible to compute histogram-based features of each sub-images of EEG signals corresponding to the frequency bands of the EEG signal rhythms. And the histogram-based features are effective for automatic sleep stage classification from EEG signals. And the classification results indicated that the Modulate wavelet kernel function of multi-class T-square support vector machine classifier had provided a 92.93% classification accuracy in sleep stages from EEG signals. And also in this work we have seen from the one dimension signal you can convert into time frequency image, and lot of image processing techniques can be used for the studying of one dimensional signal. So that gives you actually platform matrix kind of representation where a lot of matrix theory also can be applied. So this is by analyzing one dimensional signal with the time frequency approach, and that provides you image kind of representation, matrix kind of representation, where it opens a lot of doors for the study purpose. And the mean and standard deviation of Euclidean distances, which based on the 3-dimensional phase space reconstruction of subband signals, have been found useful for measuring the emotional changes of the brain. And the classification results have shown that Modulate wavelet kernel function of multi-class T-square support vector machine classifier with CL multi-wavelet had provided 91.04% classification accuracy for emotions using single channel EEG signals. And these methods also can be studied for the biomedical images. And in next talk, actually I will cover this medical imaging and use of this signal decomposition methods for the medical images analysis and classification. Thank you very much. You can have questions.
Good evening, sir. Hello. Hello, sir.
Yes, good evening. Yes.
Sir, I want to ask a question. Sir, what is the need of using different kernels in SVM as you have shown the results?
What actually? You able to see the slides?
Yes, sir. Yes, sir.
Can you see these boundaries, all the boundaries?
Yes, sir.
In this figure, these are all based on the kernels. So here, when you go for such kind of data, here, like here you can see this one. Can you see IMAP2?
Yes, sir.
This box plot. So this actually, these box plots nicely can be separated. with the simple threshold.
Okay, okay, sir.
Okay. Now, how to separate this one? First IMM.
First one, sir.
You have to have S kind of some thresholding,
Yes, sir. Yes, sir. Yes, sir.
like no S. Then only both class can be separated.
Yes, sir.
Simple. If you take simple line,
That
then both will actually both are not disjoint, so it will not work. So we
yes,
need some curve kind of separation technique, curve kind of method, curve type of thresholding.
yes, sir. Okay,
Like
okay, sir.
yes, that is the purpose of kernel.
Okay, okay, sir.
So we have linear, non-linear kernel, we have polynomial kernel, we have RBF, different
Yes.
kernels, and it depends on the feature space, the nature of the distribution of data will determine the requirement of kernel.
Okay. Okay, sir. Thank you, sir.
So we have another question in the chat box that can you please give a link to the dataset for download?
That yeah, what I will do, I will send these links to this material also to Dr. Udit, and I will also send the links for these both databases, and I think he will share this material and links with all.
Yes. So participants, do you have any other questions? And you can please
Hello.
ask. Yes.
Hello, sir. This is Bhaskar.
Yes, please continue.
Yes, sir. Sir, you use the data set from the Bonn University, Germany. Sir, I also have that data set, but that data set in, I think, EDF file format something. So I have to use some browser to convert that file into CSV format like. So how did you plot that? जो अपने EDF जो plot किया था
That
वो
is
किसमें
for
plot किया sir? I just
yeah,
want to know.
that is for PhysioNet database EDF, and there is software that will convert this
Yes.
EDF file into text file. But Bond database is available in text file. You don't need to convert them. So automatically text, you can read text file
Okay.
in the MATLAB.
Okay, sir.
Sir, I think your voice is not coming.
Hello, sir. Good evening, sir.
Yeah, good evening.
Yes, sir. When it comes to BCI application like
Pachori
Neuromark,
sir, I think your voice is not coming clear.
sir, 1 second, sir.
No,
Yes.
your voice is coming. Pachori sir, voice.
How it is clear?
Now it's clear. Yes, you can ask who is asking. Any participant?
Sir, good evening, sir. My doubt is related size of the data set when I choose one application of BCI like neuromarketing domain. Sir, generally what is a good size? That means how many subjects we need to collect process for collecting the EEG data set for this BCI related application.
For the BCI, actually, sometimes BCI problem is different kind of problem. Whatever I have explained here, that is actually we are doing training, testing on the same database. But BCI, what we do, for example, we use 5 subjects to the training the system. And once you have trained system, then you will test this on other subjects.
Okay, sir.
So that is the actual BCI. So sometimes 10 subjects are fine. People develop system with the 5 subjects, and once you have developed the system, then use for other 5.
Okay.
So the training and testing both are actually subjects are also disjoint.
Yes.
Is clear?
Yes, sir. Yes. Yes.
Yeah. In this study, whatever I have shown you, this like in case of Bond database, these signals have been recorded from 5 subjects. The 5 subjects are normal, 5 subjects are seizure free, 5 subjects are from epilepsy, suffering from epilepsy disease. And all from the entire database, we have divided them like into training and testing sets. And They are actually, maybe some subjects may be like signals may be from the same subject for training, some may from subject testing also. But in BCI, they will be disjoint. That is the actual BCI.
Thank you, sir.
So in case of BCI, if you are getting even 70% accuracy, that is also good accuracy.
Yes, thank you, sir.
Yeah, this is because this is a database and training and testing part of the same database. Both them, both are different. So 10 subjects I have seen very good databases. They have 10 subjects and 6, 7, like 5 subjects are disjoint, 5 for testing purpose, 5 for training purpose.
Sir, can we use EMD again in that area also, sir? EMD.
For BCI?
BCI, for BCI also, sir.
That University of Ulster that I visited as a visiting scholar, and that group was very good in BCI. So we actually first time that we explored EMD there. And after that, multivariate EMD also explored. That like here, whatever you have seen, you have one EEG signal at a time. When you have multiple EEG signals at a time, then you can apply multi-channel data, multivariate EMD, empirical mode decomposition. That also has been explored. So this EMD method actually it has got high computational complexity because it is based on the algorithm, and sometimes you have to go for many number of iterations. So due to that, it is less suitable for BCI. But recently, lot of actually methods have come. Maybe next talk, I will explain you this empirical wavelet transform that is based on the Fourier Transform FFT algorithm that is more suitable for such kind of applications.
Sir, thank
you. That we'll see. So that actually can be explored. BCI is a such area that in India very less work has been done.
Sir.
And a lot of work is required in that area.
Yes. I started exploring about neuromarketing, sir, one of the applications.
Yeah, is very good, actually, very good topic.
Thank you, sir.
So another question from other participant. For plotting the EEG data into Empirical circles, which software or tool you used? So I don't understand. Empirical circle means, yeah, Bhaskar Kapoor has asked this question. Can you clear your question? Bhaskar, can you repeat your question? Okay. Yes. Okay. So you're just asking like which tool did you use for plotting that circular diagram of EEG?
Yeah, that is very good. That is magnetic signal representation.
Yes.
That is Hilbert command is there in the MATLAB Hilbert, and automatically it would convert signal into analytic signal representation. So it will convert Hilbert transform plus signal plus J times it is Hilbert transform will give you analytic signal representation. So in MATLAB we have Hilbert command. It will do that work.
Okay, one more question is there. Debach's wavelet is widely used for EEG analysis. How Morlet wavelet is giving good result?
Actually, these are wavelets we are not using for analysis. They are used for the kernels. And it depends distribution of the features. It is kernel, the selection of the kernels depends on the features distribution. So the what actually that is used for the signal analysis. That is signal is like in the time domain where your signal amplitude is changing with time.
Yes. So any other questions from any participant? So I think there are no further questions. So Sir, I thank you all for your wonderful presentation. It was very simple
Such
in
case
understanding.
here,
Hello?
Yes.
So
Dr. Udit?
Yes. Can you hear me, sir?
Yes, please.
Yeah. So it was very wonderful presentation, and it was explained in very simple words. So I hope participants have learned about the time frequency analysis for EEG signal, like in different contexts, like emotion classification and seizure classification. So I thank you again for accepting our invitation for this talk. So I request all the participants to turn on your videos so that I can take a screenshot as well. So dear participants, can you turn on your video? So participants, please turn on your videos so I can take a screenshot. So regarding attendance and feedback link, so that has been circulated to you all in the WhatsApp group. So you can locate the link there and please fill the attendance and feedback form. So I can take a now screenshot. Yeah, it's fine now. Okay, thank you. Thank you, sir, for the nice presentation.
Thank you. And thank you for the opportunity. And I would like to come my participants for attending this session. And also, if in case any queries, any questions, please feel free to ask me, and they can write an email to me. I will be happy to answer these queries. Thank you very much. Thank you.
Thank you very much, sir.
Thank you.
Okay, so now we'll close this session, and tomorrow we'll meet 9 a.m. again. So please fill the attendance and feedback form. Okay, so that tomorrow's link will also be communicated to you in the WhatsApp group, and it has already been sent to you all in the email also. Okay, so I am closing the session. If you have any doubts, then you can please ask. Otherwise, I'll close. Okay, it seems that there are no further doubts. I'll close the. Yeah, hello, Bhagat. Yeah.
No doubt, sir. Thank you.
Okay, fine. Thank you all. So I'm closing the session for today.